Thank you very much. As you said, my name is Justin Brandenburg. I'm with MapR Data Technologies. A little about me, I'm based in Washington, D.C. I'm part of our professional services group. We're a pretty small group. Who here is familiar with MapR? Few people? Okay. I'll get into that, more about what MapR is in a little bit. But yeah, about my background, based in D.C. Before I joined, I've been with MapR for about 2 years now. And before that, I supported the U.S. intelligence community for 7 years in a variety of different roles. But currently my role with MapR is to help our customers work with their data science teams to help them scale their models, move them into production, take them off of R&D or dev clusters, help them either scale them out, maybe work with the pipelines and the ETL that's necessary to get their data in the proper format. And then also I support some of our sales initiatives for pre-sales engagements, use case discovery, solutions, things like that. And one of those particular use case discovery and solutions is what I'm going to talk about today for one of our manufacturing customers. So what is MapR? MapR is a big data technology. Reference to being able to, essentially Hadoop, NoSQL database, streams, Spark, all of that. All of it's done on a single platform on MapR. MapR is production ready. It's resilient. It scales efficiently. It scales reliably, and it's stable. And what kind of a distinguishing component about MapR is that it doesn't really matter the data. I like to think of it as a kitchen sink, and I can dump everything into it. And from there, I'll worry about what I need afterwards. So I don't worry about schema. I don't worry about data type. I don't worry about whether it's an image. I don't worry about if it's a video file. It can all go in. So it makes it a very versatile platform. And so I like to think of it as a general platform that can be customized to a specific domain, specific industry, to solve really hard, challenging problems regarding both data and analytics. In addition to that, it can integrate with basically any tool. So the engineers at MapR kind of realize that we don't know what we don't know yet. There could be an awesome tool that comes out or an application that comes out next year, and we want it to work on MapR. So we have an open API system that basically I would say 99% of things can plug into. So the way it works is MapR would essentially be the platform that you would build stuff on top of. You would, if you're a BI organization, you'd put your Tableau on top of that. You had clicks on top of that. You would run your Spark jobs on top of us. We have integrates Spark that integrates with MapR already. So you don't have to download it or install it separately. It's already integrated in the cluster. We're cloud agnostic. So we install on AWS, we install on Google, we install on Azure, and we install on bare metal. You can have one cluster on AWS and one cluster in Google, and they can replicate back and forth. If you want to, at one point, leave AWS and go to Google, just lift up your plate, put it on a new table. That's essentially how easy it is. So there's kind of prevent cloud lock-in, which is very important to some of our customers who have competing commercial ideologies and their competitors in specific markets. But what I want to talk to you today is about one specific one industry, manufacturing, commercial, things like that, and kind of what's going on right now is the emergence of Industry 4.0, and that is the adoption of IoT. And the IoT of all these smart devices, all these new things are going to be capturing new data, and this is integrating a whole host of new problems. Well, I wouldn't say problems, but challenges. One, massive amounts of new real-time data, giving you greater insight to what's actually going on into your current business processes, your manufacturing processes, security processes. What this does is it gives you greater insight and greater efficiency, but it also gives you greater abilities to have greater insight to what's going on in your organization. But it also leads to another host of problems in terms of security, data capture, data monitoring, efficiencies in data storing and warehousing. So one of the things that organizations have found that is to kind of cut costs as they capture this new data, they need kind of a universal platform that can kind of capture all this data and use it reliably, capture real time in both batch and streaming data, and then analyze it in real time as well. So today I want to talk about predictive maintenance. Kind of the main goal of predictive maintenance when it comes to IoT, manufacturing, things like that, is you want things to operate more efficiently. You're trying to avoid downtime. You're trying to identify if there's going to be some failure along any part of your supply chain, any part of your manufacturing line, any part of some sequence of processes that you have going on. Because basically, if any part of those goes down, it's going to cost you revenue. And that, when it starts to affect the company's bottom line, that's when they start to listen. That's when they start to pay attention. We had an auto manufacturer that last year became one of our customers. And when we met with them here in Texas, they put out a new car every 58 seconds, which when they told me that, I was astonished. But it's because they've streamlined all those processes so well that it's just a machine, and it just runs and automates. But when something goes down, and if it's something in regards to either their manufacturing components, or if something irregular occurs, and when some components are being painted because there's an increase in temperature that they haven't been able to account for, that affects the paint color and how it goes on the side of the car, that costs them money. And if it goes down for a certain period of time, it costs them a lot of money. They had a bit of a bump, went down for a couple hours, it cost them $500,000. So it's a very, very big deal, and people are very, very focused on it. With kind of the new integration of IoT and smart appliances and being able to capture data, it's important to know that kind of data is generated one event at a time, and over the course of time, so whether it's a transaction or whether it's a video frame or an image or something like that. And so you want to be able to capture this and catalog it and look at it and refer back to it, be able to look at the data in its raw format, and perform any ETL that's necessary as it comes in. But what do we do now that we have actually been able to do real-time monitoring? Because it's not just one or two devices that's pushing into a topic or a stream. It's pushing multiple. And so if all these different things are pushing data at a specific time, you want to be able to capture all this. MapR is kind of a great platform for this, because what we've done is we've taken the HDFS file system, we've taken the NoSQL database, and we've taken the message broker for real-time streaming, and we've put it all into a single cluster. So we've made it a single entity. So there's no longer a separate cluster for HDFS. There's no longer a separate cluster for NoSQL database / HBase. There's no longer a JSON document database. There's no longer a Spark cluster. There's no longer a Kafka cluster. It's all one cluster. And so that removes a lot of the inefficiencies in cluster administration that you have to deal with, in addition to focusing and managing your data. So now you can just focus on monitoring your data in real time. But what is monitoring really telling us? Monitoring is just telling us what's going on. It's just telling us, giving us a window view of what's going on with our current processes. It's giving us a window view of what's going on, for example, network security. It's giving us just an idea of who's accessing our network, the different flows, things like that. We have customers who are oil and gas. They have smart devices that are attached to their fields, their oil and gas fields. These things that you're capturing temperature, volume, all these different dynamic components in real time, and it's being captured and sent to MapR. The great thing about MapR is that it can be bundled up into edge computing. So in limited Wi-Fi or connectivity environments, these things are all captured in real time and stored and queued, and then once connectivity reestablishes itself, it feeds back up into the central data store. which is something that is pretty valuable for not only remote locations for oil and gas, but also forward operating units within the US military. But to the extent of when we're monitoring, all we're doing is to making sure everything is behaving normal. And what we're monitoring is making sure everything is healthy. But to be able to extend to make sure that can we maintain what's going on? Is it going to remain healthy? Can we predict if something is going to identify if our system is going to go down or something irregular or non-normal is going to occur? So we want to be distinctive between classification versus prediction. When I was in grad school, one of my classmates, he was able to run RNNs for anomalies across EKG data. So he can identify irregularities in a person's heartbeat to identify if maybe something's going on, if they're showing any indications of health issues. And it was very, very interesting, and it was great how he did it. And he did it on a small data set, but what he was doing was just identifying non-normal behavior or non-normal instances. And all you could do at that point was classify them. And on EKGs, they're a lot more challenging to identify if they're non-normal. And some data sets like this, they obviously stick out. I mean, we can definitely see that when something is non-normal or irregular with our data. And we can classify this as, okay, this is definitely not normal. And since we know this, we have an idea of what to look for. But now our goal is we want to predict when this will occur. So we want to forecast if any of these non-normal events will happen. When we want to predict these type of non-normal events, especially for industrial devices, we want to do it to prevent unplanned downtime, which could affect, like I said before, unplanned or revenue loss. If it affects the bottom line, people are going to care. One of the issues that I felt before I joined MapR was that I'd get my work and I'd go do it over in my sandbox, similar to the video that was on Monday, which is awesome, by the way. It kind of really hit the note. But what it just describes is when I get my analysis and I've optimized my models and I've generated my insight, what's the next step to utilize it? What's the next way to convey it? And getting somebody to care, a decision maker to care, is part of the process. And if one way to get them to care is by telling them this will affect the bottom line, this will reduce revenue loss, and this will make you look good, then they'll start to pay attention. But we don't want to do predictive maintenance for just one device. We want to do it for a factory of devices. So a solution needs to scale. It can't just be for one or two. It can't just be for small data sets. It can't just be for a single workflow. It has to be for thousands of devices. It has to be for an entire factory. It has to be for multiple factories. It has to be able to capture all the data in real time. You have to be able to refer back to it to then optimize and then re-update your model. All these things need to be taken into account when you're developing a model, when you're developing the algorithm that you're looking at. Because if I'm developing a model and I optimize it just on my local laptop, and I'm using it in a specific data set, and then it doesn't translate, then what was the point of all the work that I just did? I need to know the broader scope. I need to know the architecture that I'm going to be working on. I need to know how this will convey and be re-implemented, and who will be using it, and how they will be interpreting my results. So some of the solution building blocks for this particular use case was MapR, Spark, Python, and TensorFlow. It's not 4 basic components that, when you put them together, can be very powerful. The key component, at least in this case, was the MapR converged data platform. One of the things I described earlier, we have our own proprietary file system. We have our own NoSQL database that is both key value as well as JSON. And we have our own Streams message broker called MapR Streams, and which is similar to Kafka. And then we have seamless integration with Spark because our engineers have already taken Spark and worked so it is already integrated with the MapR RPMs. And then you can install Python, you can install R, you can install any analytical tool you want. You can install TensorFlow, you can install MXNet, you can install any deep learning framework you want. And it can be both on bare metal and in the cloud. And it can have basically any visualization tool that you want on top. We're not a visualization company, so basically, if whatever tool you want to use, you can use on top of us. Kind of understanding the workflow is understanding, how is the data going to be used? So we want to be able to look at, we have data coming in, we have people pushing it out, but we want to control everything and make it so it's seamless and foundationally stable in all this part in the middle. So you can leverage all these different components and develop some interesting and production-ready analysis and projects and deployments in real time by leveraging all the things that are in this box. So you can push stuff into MapRxD, which is our file system. You can do all the processing batch processing using Spark. You can query it using Apache Drill. In addition to that, you can be pushing new data into MapR Streams, which has specific topics that you can then customize and do processing on in real time via Spark structured streaming. You can push it, once it's ETL'd, it can be put into a structured state. It can be put into our MapR database. And it can also be populating in visualizations that a user can access. In addition, you can export and create new flat files, CSV files, Parquet files, different data types as needed. So it gives you a lot of flexibility in how you want to analyze your data. I don't think I needed to talk much about TensorFlow, but I chose TensorFlow for this particular problem because 1, TensorFlow is super popular. 2, it's got a lot of documentation. 3, it's got a Python API, which I use mostly Python basically all the time now. And so of all those things, it was kind of like a natural decision to choose TensorFlow for this model. I'll go into why I chose RNN in a little bit, but the fact that I chose TensorFlow, it leads to the fact that I think Google realized that to get greater adoption for TensorFlow, that they just had to flood everybody with all kinds of documentation, so textbooks, blogs, different forms of blog posts and things like that, just to give everybody a variety of different examples. And to that extent, I think it's been very successful because that's why TensorFlow is probably one of the most popular frameworks out there. What is a tensor? It's an array, it's a matrix. It's just a way to kind of munge your data, get it into different forms, and be able to push it into a different model. Kind of touched again, why did I choose TensorFlow? It works both on CPUs and GPUs. It's got higher abstraction now with version, I haven't even been able to check out version 1.7 that I think that got released a couple of weeks ago. I mean, I still have been working on some stuff with 1.5, but I haven't been able to really investigate what they've done with 1.6 and 1.7 yet. But it's got a lot of development, a lot of increased utility for function abstraction. And it's very lean. So once we've talked about a lot of the accelerating the training of these models, on GPUs and things like that. But once the model is actually trained, it's very lightweight and can be extended and pushed out to different edge computing devices. So it doesn't necessarily always need like the heavy processing of GPUs. In some instances, it does if you want to leverage the GPUs for streams for like incoming video feeds, so you can analyze frame by frame, face recognition. And the good thing about MapR is that our data fabric extends to both CPUs and GPUs. So you can install both MapR on CPUs and GPUs and leverage the file system to populate all your data that feeds your batches that are pushing all the data into your GPU for the modeling. One of our other data scientists presented a real-time facial recognition model at Strata a couple weeks ago, leveraging the GPU. And he took the trailer for 3 billboards outside of Ebbing, Missouri, and built a model that every time either Frances McDormand face or Sam Rockwell's face came up in the trailer that was being pushed through MapR streams, a bin box came on and with a percentage score saying that this is 57% confidence that this is Sam Rockwell, or 57% that this is Frances McDormand. And he was able to push that and run it on a GPU. These are kind of the 3 most common implementations of deep learning frameworks. So like I said before, I've settled on recurrent neural networks for this problem. And I'm going to jump ahead and then jump back real quick. So kind of go through the process of how I was looking at this data. So essentially, our customer came to us, and they're like, look, we're a manufacturing organization. We have all these devices that are performing in these specific functions, and we want to identify when one is going to need maintenance to essentially prevent downtime. So the devices they had in question were these things called SCAR robots, these arms. And these things can perform a variety of functions. They're at rest, and then when they actually are performing an action, it could be screwing a screw along an assembly line. It could be painting something along an assembly line. Just any number of kind of consistent, continuously performed acts. But when it's either in action or at rest, it's just always in this case. And so you'll see a variety of different positions and metrics associated with whether it's in rest or in action. But it's done sequentially. It's done over time, and it's captured in specific timestamps over time. So that led me to look at this from a time series perspective. So with time series, there's a couple of different ways that you can use for forecasting your prediction. My background's in econometrics, so I used to do a lot of ARIMA models, a lot of forecasting of like GDP data and stuff like that, forecast horizons, moving averages. But typically, when looking at this type of data, you look for trends. And part of the issues that we kind of saw with this data was that we didn't see a lot of trends. And that came after I first looked at the data. So they gave us the data, and it was just kind of raw format. Didn't really know what we were working with. This is kind of the workflow that I'm going to describe coming forward. It's kind of the entire data science workflow that got me through the problem evaluation to the actual solution. So first, I just need to they sent over a bunch of data, which was in just .dat files, which could be anything. So I didn't know what I was working with, because they literally didn't give us any background. It was essentially somewhat of a bake-off. They didn't say that who we were in competition with, but I have a feeling they didn't really give out a lot of information. They said that here's your data. This is from this type of device. Find us a predictive maintenance model. So I needed to be able to look at what was going on in this data. So they sent over 2,000 files, and I dumped it into MapR FS, which is our file system. It was already in a compressed format. Was able to unzip it. Looked at what was going on in the actual DAT file, and saw that it was in XML. So this is a snapshot of like the raw data in its XML format. So how am I going to process this data? I want to be able to process it in bulk, because it's just a bunch of files that I just need to be able to look at from a top-level view. So I decided to use PySpark to do this. A good thing about it is like PySpark has an XML format package that you can essentially do bulk conversion if you take all these XML files You can put them into a data frame. And from there, it gives you a lot of options of how you want to look at your data. Before I had to put it into XML, though, I had to first convert all the DAT files into XML format. And that was just a process of just changing the extensions. And if you have a little bit of Linux and command line experience, it's literally only a couple of bash commands, and it's very easy to do. So all standard bash commands and Linux commands work on MapR. So went and got those commands, did the conversions, converted them all from DAT to XML file format, spun up Spark, literally 4 PySpark commands, ingest, using XML package, convert to a data frame, and let's take a look at what we get. Just the original, not without touching it. The figure on the left gives me a very long, narrow data frame. And what it did was, it gave me 28, for every timestamp, I have 28 rows. So the first timestamp took 28 rows, the second timestamp took the next 28 rows, the third timestamp took the third 28 rows. So essentially, at each timestamp, 28 different metrics were being recorded. So, but this was challenging to look at and understand. So just by adding a couple more commands into my PySpark code, I was able to pivot the table. So now each one on the right here is a little bit more challenging to read, but each line is a timestamp, and each column is a specific feature or a metric that's being captured at each timestamp. So there's only 4 listed here, but there's 28 in total. So now I can actually see what's going on with my data. I can actually look at what's going on here, how big is it, what's the total value associated, the number of rows associated with all these XML files that I was given. Turns out it wasn't that many. It's approximately 80,000 timestamps. So I decided to export it into just a CSV file and then start playing with it with Python. Cool thing about MapR is that you can use any notebook tool you want. So if I was an R user, I could have used RStudio, but I'm a Python user. I've been using Anaconda for several years, so I kind of default to Jupyter, and you can install Jupyter and Anaconda on MapR, no problem. And I use Python 3.5, and so I spun up a notebook, and I started doing my data exploration. Kind of seeing the data I was working with, kind of getting an idea of the different types of visualizations, and kind of see what was going on. Started to notice that, okay, this is a time series problem. Each metric has its own kind of thresholds of acceptable behavior, but then with each metric, there was also an extreme event. One thing I noticed that the extreme events were the same at the same timestamp for all features. So it wasn't just that timestamp 26, metric 2 would have an extreme event. At timestamp 26, all metrics would have extreme events. So it made it a little easier because now I can start to make some assumptions that if something extreme is going to occur, it's going to happen across all different positions that this device gets captured at. Now it comes back to, okay, if our data looks like this, what type of models or approaches can I use to predict if some sort of extreme event will occur? So going back to recurrent neural networks. So I mentioned before, my background's in econometrics, so I was looking at ARIMA models for forecasting. But with ARIMA models, you typically, there's some sort of trend associated with the data. And you want to be able to look at different forecast horizons. You want to be able to take the whole data, look at moving averages, regress retroactively on specific components, and be able to look at whether my forecast falls between some sort of threshold. There wasn't really any trend associated with this data. Either it fell between 2 values, or it was extreme. So looking at it from a REMA perspective wouldn't have been a very good solution. Next, I considered a Kalman filter. Kalman filters are great for looking at objects in space and kind of predicting, trajectory. They typically reduce noise. They zero out any noise, so you can just look at just kind of positions and then forecast if all things considered, that position will not change. Again, that wouldn't have necessarily worked well with this data because Kalman filters are only really good with linear data. This data was behaving somewhat nonlinear. And so I've been looking back on, at the time I was, I'm a newcomer to some of the deep learning initiatives over the last year. But I've been reading a lot more about recurrent neural networks, especially to sequence to sequence to sequence, and how they're very good for predicting the next letter in or next word in a sentence, or the next value in for example, time series if you're doing it for financial forecasting. So I decided to apply kind of that logic for this particular problem. Kind of looking at the different topology. But one of the things one of the reasons I kind of chose the RNNs was that because the RNN is not really looking at, parallelization of matrix multiplication across multiple matrices, it's kind of still a sequence process that the CPU could still be optimized to leverage that. If this was an image problem, I probably wouldn't have chosen this particular method to do it, but I was also looking at, I was like, well, how is this going to scale? Is this going to be effective across multiple devices? And the good thing is that it can scale. It can be distributed out to multiple different devices, and it can be embedded in multiple different types of CPUs. Because I can't turn around and give our customer a solution and tell them they have to go buy a bunch of new hardware, because they're not going to do it. It's not going to work for them. I have a feeling in the next couple of years they will, but at the time it's just not in their budget. So I start evaluating, choosing TensorFlow, and then start working on developing my RNN model. I set up my parameters, I set up my batch sizes, start testing and training my model and kind of seeing how it does in terms of the effectiveness of my forecast. So similar to, like if I was just using a REMA forecasting model and I want to compare my forecast to actual, I do the same thing. I took out the last 500 timestamps and I compared my prediction to the actual timestamps, and that's what you see right here on the bottom. But I was able to kind of iteratively test my model, run it, choose batch sizes, different things, and kind of come up with a solution that could work pretty well once it's been optimized. And that's the other thing. I only had about 2 weeks to do this, so I didn't have a lot of time to optimize. Whether I chose a basic RNN because I just wanted to make it as general as possible. I didn't have a lot of time to choose whether if an LSTM would be more effective. But luckily for me, the basic RNN was actually very, very effective in predicting extreme events. It got very close to whether a specific timestamp was going to have something way outside our threshold than if it was going to be within the threshold. And that was the goal. The goal was, based on my historical analysis, I could make some assumptions that as long as the data was my forecast was between 400 and just over negative 200, then there would be no alert. But if my forecast exceeded these safe thresholds of acceptable historical behavior, then I wanted someone to be notified. I wanted someone to know. I wanted an alert to be raised. And I wanted to be able to generate this ahead of time before it could occur. Now, these timestamps were coming in milliseconds. and another basic problem with it, it wasn't uniform milliseconds. Sometimes it was, 500ths of a millisecond, 300ths of a millisecond. There wasn't any uniformity, so it was very challenging to kind of come up with a specific forecast horizon. So in this particular case, I just chose a one-period forecast with the assumption that, okay, I'm not a manufacturing subject matter expert, but if these guys can make some assumptions based on, well, if they get one alert, okay, maybe that's all right. But if they get 10, then they need to be able to plan ahead of time, okay, we need to take this one offline. So after 10, maybe around alert number 7, they're like, okay, we need to prep and have the other one ready to be able to switch out these components when necessary. So it's getting them a notice to let them know that this is going to happen. Deployment. So now I built my model, but it was on batch data. It was on historical data. I needed to be able to now take my model and be able to deploy it on new real-time incoming data. That's where MapR Streams comes in. MapR Streams leverages the same Kafka API that you'd see on standard Kafka clusters. Good thing about MapR Streams is that while Kafka has somewhat of a topic limit of around 500 topics within a particular stream, MapR can handle tens of thousands of topics resiliently, stably, because it's all built into the hard engineering of the cluster. So a single factory that has thousands of these machines could take my model and set up a specific topic for machine 1, machine 2, machine 3 in a single stream and be processing all these with my model in real time. Because all I did, now that I checkpointed my model after every 100 epoch, and then once I got to what I thought was the lowest means RMSE, all that data associated with the weights, the metadata, the model, the components, everything like that was checkpointed back into the cluster. So then I created a consumer. And if you guys are familiar with streaming technology, you have a producer, you have a consumer, you subscribe to topics, the consumer subscribes to topics, the publisher publishes the topics. So I created a consumer that had a topic that subscribed to a stream that would then ingest new data as it comes in, and it would pull my model that was saved on my cluster and be able to stream the new data through as if it was a filter. And then it would output the results of my model and give me my prediction. The good thing about this is that a consumer can also be a producer. So it can also populate a dashboard. I actually did all this. I stopped at this point. I was like, hey, guys, here's your solution. And then they were like, well, what does this mean? You have to make a visualization. So I was like, damn it. So I had to go back and spend 3 days just building this stupid dashboard. I don't know. I understand the visual component. It's a necessary component. It's important. This is just using Plotly. Plotly is just an online interactive dashboard tool that's got Julia, Python. I think it's got some R APIs, but it has streaming tokens, so you can actually set up a streaming dashboard and be able to pull in real time data that's coming from your model. I'm running low on time here, but let me run back. I didn't tell you where I was getting the real time data. So I don't have a SCAR robot. So I had to use what I was working with. And so I took all the DAT files I noticed were in chronological order. And so I took the last 10 and set them aside in their own directory within MapRFS. And that was going to be my real-time data. And I wrote a producer script that looped through these DAT files, converted them into XML format, converted them into a dict, and then converted that dict into a message, which then was sent to my stream. And so then I was able to essentially have real-time data that was being fed into my consumer to show the real-time prediction and actual data on my dashboard, be able to show the alert that's populating on the screen, in addition to being a person who's monitoring these devices, either a text message or an email. My boss actually extended it, and he had it actually sending it to his Twitter feed, but I didn't think that was that good. But being able to receive a text message in real time to say, hey, this device 27 is on its third predictive failure notification, you need to probably prep to get this offline, especially when a guy's working on the floor, increases a lot of the efficiency of preventive maintenance and reducing overall cost. The good thing about this is this model, that was just, my consumer was just a script, but that could have easily been packaged up into a Docker container. It could be packaged up and then deployed on an edged cluster. It could be packaged up and deployed in a variety of different ways. And it didn't even need to be TensorFlow. It could have been MXNet, which is one of our other data scientists. Like, he's a huge MXNet fan. He thinks it's way better than TensorFlow. But then you also Torch or any of these other tools. And even if it hadn't been TensorFlow, even if it had just been a standard scikit-learn. So even though you're on a big data platform, because of the way the data is coming in and the process and the pipeline and everything like that, it's very narrow and focused. So you don't necessarily need to use something like Spark. You can still leverage some of the smaller data set tools, but be able to deploy them in a useful fashion. Just some points to remember. TensorFlow is just one tool. There are many. I approached this from a top-down level. Was it supervised or unsupervised? How was it looking at data? Was it classification? Was it prediction? Was it regression? Is it time series analysis? How is this going to scale? So this model is so general that it can be extended to thousands and thousands of devices, and then each of them can be tweaked and adjusted for their specific purpose. So not every SCAR robot is just going to be screwing a screw on the assembly line. Not every SCAR robot is going to be painting. So some of the metrics are going to be different. So each one can be adjusted and customized as needed. But it'll scale, and it'll all be able to scale in real time and be able to process in real time. And so a network manager or a maintenance person can focus on just the ones that are showing indications of failure. A lot of this was understanding the logistics of how my machine learning was going to be used. So we have, MapR has a free ebook that kind of discusses this. Ted Dunning is one of the 9 board members on the Apache Foundation. He's also our chief application architect. Super brilliant, nice guy. But with the understanding that data analysis doesn't happen over in the corner, you need to be able to understand where it fits in the entire logistical pipeline of your organization to be able to really increase the value and the insight generated by data science. That's data scientist's job, is to be able to pull value and insight from data. And for an organization to actually get the most out of that value, they need to be able to convey it in the proper infrastructure and architecture. So logistics are very, very important. I wrote a blog post and put it on MapR, our blog, that kind of goes into this presentation in greater detail, as well as all the code and everything, and links to it are on GitHub. So if you go to the MapR blog, all the links and stuff will be there. And we also have a MapR Academy that kind of goes into, it's our free online training. It kind of goes into big data technology, Spark, developing Spark applications, introduction to NoSQL databases and things like that. And we also have a sandbox so you can actually test out a lot of this stuff. And I think that's it. So do we have